Similarly, being a partition of sample space. Now, this is a total sample space. Possible outcomes are there, and we are making partition of this. Now, nothing should be common. Second part, maybe the third part, and so on and so forth. We go on making partition. Now, out of this partition, suppose okay, what we see, like all these partitions. If I say E1, E2, E3 like this is E1, is E2, this is E3, and all the way I go up to En. So here we are saying it by Ei and Ez. So we see that none of the two, nothing is common in these any of these two events, E1, E2, E3, En. That we write this way. Ei intersection Eza would be phi for I is not equal to J. Because if I is equal to J, it will E1 intersection E1, that will be E1 only. But for I is not equal to J, and Ij can be 1 to n. N partitions we have made, so Ij can be from 1 to n. And secondly, all the union of these all partitions event should be a sample space. The total rectangle here represents this. And PEI should be greater than 0. The probability of either of these partition event, E1, E2, E3, En should be greater than 0, right? So it means the partition E1, E2, E3, En represent mutually exclusive and disjoint event. Disjoint event means they have nothing in common, and they are mutually exclusive, and of course exhaustive also. Exhaustive means if I take the union of all these two statements, the union of all these will be sample space. This means exhaustive. It means exhaustive, and this means mutually exclusive. Okay? The intersection is um, EI intersection is phi. That means they are mutually exclusive. Look, and we understand the partition of sample space. We can make any number of partition of the sample space, and but those partition event, if we define them as E1, E2, E3, En, they should be disjoint. There should be nothing common, and they should be mutually exclusive. Means their union should be sample space. Okay. Okay. Then any event like this, and this is E. Outside of this E is E complement. Now see, this is the total sample. Now obviously E and E complement, nothing is common between inside and outside. So it satisfies this condition. Also, when I take union of the E complement and E, I get S. I get the entire rectangle. Right? Yes. So that means E and E complement also form partition of sample space. In the previous example we saw we made n partition. Here we're making just two partitions. That means partition is not unique. We can make a partition in many ways. All right. So let us take another example here. So E and F are only two events in this case. So let us represent these two event E and F in the Venn diagram. That thing will be everything outside E and F. Everything outside E and F should be this portion. Yes, this portion here. This will be E complement intersection F. If we notice carefully, all these events, E intersection F complement, E intersection F, E complement intersection F complement, E complement intersection F complement, and E complement intersection F, they all are mutually exclusive. There is nothing common in any two of these events. And also, they are exhaustive. That means when we take the union of all those, we get S. That means they also form a partition of sample. Partition means we just understood it means dividing the sample space into certain numbers of equally exclusive and okay. So we understood now what is the partition of sample space mean, right? Now we will continue our discussion for the theorem of total probability. Now, to discuss the theorem of total probability, this is also an important theorem over here, theorem of total probability. Now, let E1 into En be the partition of the sample space, which we have already understood what exactly the partition of sample space means. Our sample space is divided in n parts. And partition of sample space, suppose E1 into E3 has non-zero probabilities, of course, of occurrence. Let A be any event associated with S. Now here we can take A any event which is associated with this sample space S. Let's draw this event here in A. Now this A, probability of occurrence of A will be E1 A by E1, E2 A by E2. Okay. Let's see this situation here. Let's make the partition of this sample space. Suppose I make one part, and then we make second part, and we make third part, and we go on doing up to nth part. This will say En, 1, E2, E3, and this total is the sample space. All right. Have n events here, n partition of that sample space, and the event A, you can see here, A is this event. Now A is any event associated with S. Now then PA is given by this. This is what the theorem of total probability states. Let's see how did we get this. Now A can be, sorry, the event E1, E2, E3, and En all together make the sample space. So I can say S is equal to E1 union E2 union E3, and it goes up to En. So that's the sample space. S. Now what would be A? See, this event A will be E1. I can say S intersection. Yes. We can say A is equal to A intersection S. A intersection S. And what is S? S is E1 union E2 union E3. So it can be written as A is equal to A intersection S means E1 E1 union E2 union E3, and it goes up to En. Now if we apply distribution of this intersection on union over here, this comes A intersection E1 union A intersection E2 union A intersection E3, and this goes up to A intersection En. All right. So now if we would like to find this PA, total probability PA will be P A intersection E1 union A intersection E2 union A intersection E3, and so on. You can look in the Venn diagram itself. A intersection E1 is this part. A intersection E2 is this part. E intersection E3. They are different. For the disjoint event, their probability would be sum of these. This will be P of A will be P of all this, and P of all this can be written as PA intersection E1 plus PA intersection E2 plus PA intersection E3, and it goes up to probability of A intersection En. Now, from conditional probability, we have already learned PA intersection E1 can be written as PE1 into PA by E1, right? This thing can be written as PE1 into PA by E1, right? The second part, this thing can be written as PE2 into C. This part we got PA1 A by E1, and plus this thing can be written as PE2 into PA by E2. Okay, and likewise, we can also write the third part P. This goes on up to N plus PE3 into PA by E3. So this is what the total probability theorem states. It goes up to PEN into PA over EN. So let E1, E2, En form a non-empty event with which constitute the partition of sample space S, and E1, E2, En are pairwise disjoint. I mean, there is nothing common in any one or any two of these event E1 to En, and their union is S. That's how we said the partition. That's what we discussed. The partition of sample space mean these two conditions should be met. It might has come from any one of these, right? Event A might have come from this part, this part, this part, that part. What is the probability that it came from the particular EIth, E1, E2, E3, and so on? So to get this, we would try this formula of conditional probability. That's right, the formula of the conditional probability. What did it say? PEI over A. PEI over A is same as PEI intersection A divided by PA. So PEI intersection A by PA. From the multiplication theorem, PEI intersection A can be written as PEI PEI into PA over EI. This is multiplication theorem of probability. PEI into PA over EI divided by PA. Now, PA is the total probability of the event A that we saw in the previous case when we found the total probability of A. PA was actually the sum of all those PA, E1, A by E1, E2, A by E2, and so on. So we write in mathematical notation like this, sigma, say J is equal to 1 to N. So I'll go from 1 to N. So PEJ into PA over PJ. All right. So this is the value of PA. If we substitute this value here, I get PA over EI is equal to what? So PA over AI is equal to EI, A by EI divided by this quantity here. We could write it here. This is like PEI into PA over EI divided by denominator. I want to write all that the sigma notation. Sigma j is equal to 1 to n. Okay, j is equal to 1 to n. PEJ and PA over EJ. Right? Bag 1 is selected, and E2 is even that bag 2. Bag 2 is selected. After we select bag, we draw the ball. So E is the then A is the event that a red ball is drawn, found to be red. Right now, A is the event. A we define as a red ball is okay. Now, what is the chances? Like we have the two bags, and obviously it will be equally likely to select either of these two bags. So the probability of drawing bag E1 and probability of drawing bag E2, selecting bag E1 and E2 will be same, that is 1 by 2. Once I select bag E1, then from E1 okay, how do we write that thing as drawing 1 second. drawing a red ball from bag E1, right? Bag E1 is selected, then we draw the red ball. The probability for this will be if I have E1, the first bag is selected, and the probability of drawing red ball would be 3 is favorable and total is 3 plus 4, 7. Similarly, we can write PA over E2 means if the second bag is selected and drawing a red ball from the second one. So 5 by 11 because favorable are 5, total are 11. Find the probability that it was drawn from second bag. So what they are asking P E2 over A. E2 over A means ball is drawn from bag 2. The ball is drawn is found to be red, and then we want to know what is the probability that the ball was drawn from bag second, and for that we will use Bayes theorem. So Pe2 by A will be what? By Bayes theorem, Pe2 by A will be Pe2 Pa over E2, Pe2 into Pa over E2 divided by sum of all the event in the denominator, right? So PE1, PA by E1 plus PE2 into A over E2. We just have to partition of the sample space here, E1 and E2. So this will be E2 means 1 by 2 into A by E1, 3 by 7 we had, yes, 3 by 7 divided by E1, this is E1, right? Okay. E1 means half, A by E1, A by E1. Oh, A by E2 was 5 by 11. This value here, A by E2 is 5 by 11. 5 by 11. So 1 by 2 into A by E1. A by E1 is 3 by 7 plus 1 by 2 into A by E2. That is A by E2 is 5 by 11 again. So we can take 1 by 2 common and cross it out. So it comes like 5 by 11 divided by 3 by 7 plus 5 by 11. 3 by 7 plus 5 by 11. We took 1 by 2 common and crossed it. And then it comes like 5 by 11, 77. So that's right. 5 by 11 divided by 33 plus this was 5 by 11. 5. So 33, 33 plus 35. 33 plus 35 will be 68 by 77, which comes out to be 5 7 35 by 38, 35 by 68. So 35 by 68 should be the probability that it was drawn from bag second. Okay, so next we have given 3 identical boxes, 1 to 3, each containing 2 coins. Now, in the box 1, both coins are gold coins. Box 2, so let's quickly draw the box. Here you have 2Z, both are gold. And the box 2, we have both coins are gold. In box second, both are silver coins. So 2 silver coins, and there is 1 gold, 1 silver coin. Both are silver coins, and in box 3, there is 1 gold, 1 silver. Gold and silver. Okay. A person chooses a box at random. So the box are similar, so it would not be possible from outside to tell which box contains what. So a person chooses a box. There are 3 boxes, so the probability of it choosing either of the box would be equal. First, second, third. That means probability of selecting box 1, 2, 3 will be same. So means each has the probability 1 by 3. Now what is the probability that the other coin is gold? E1, E2 and E3 represent um, selecting box 1, 2 and represent selection of box 1, 2 and 3 respectively. Okay. Now, of course, PE1 would be equal to PE2. They are equally likely events, and which will be equal to PE3. So all of them would be 1 by. Now, what else? A person chooses a box selected that the coin is gold. What is the probability that the other coin in the box is also gold? Let's say A is the event that the coin drawn is a gold. So we'll define event A as coin drawn is of gold. Okay, the gold coin is drawn. So A is the event that the gold coin is drawn. Now E1, E2, E3 is given, PA is given. So can we calculate, can we say P A by E1, A by E2, A by E3? Yeah, we can get that. So PA by E1 means when the E1 is selected, what is the probability that the gold coin is drawn? A by E1. So there are two gold coins and the probability of drawing a gold coin in this will be uh, 2 by 2. 2 by 2 means 1, definitely. Now PA by E2, PA by E2, coin drawn is a gold in this. In this, we do not find any gold coin. So there are 0 gold coins, 0 by, so it's 0. 0 by 2, 0. What is PA by E3? A by E3. Coin drawn is a gold from this one. So there we see the one coin is of gold. So there are total two coins. So 1 by 2. Now they're asking what is the probability. Now they're asking what is the probability that the other coin in the box is also gold. That means they're asking what is the probability that the coin was selected from box 1. Okay, that means we need to find P A over P E1 over A. P E1 over A. Now by Bayes theorem, this can be said as PE1 into PA over E1, this divided by the sum of all the probabilities. PE1, total probability in the denominator, right? A by E1 plus PE2 into PA by E2 and plus PE3 into PA by E3. That's what Bayes theorem says. All right. And if we put these values over here, what do we get? Okay, let's get these values down here. So it comes E1, which is 1 by 3. 1 by 3 into A by E1, which is 1 divided by 1 by 3 into 1, 1 by 3 into 1 plus 1 by 3 into 0 plus 1 by 3 into 1 by 2. So this calculation here gets like becomes 1 by 3 divided by 1 by 3 plus this is 0, so this becomes 1 by 6. So 1 by 3 divided by, here you take LCM 6. So it becomes 2 plus 1, 3 by 6, and which is 6 by 9, and which should be same as 2 by 3. That means the probability